Hello, today we're going to do derivative shortcuts. So all those limits that we did in the last chapter, we have found shortcuts for. So our first idea that we're going to look at is just a constant. So if I take the derivative of any constant, what's it going to be? So if we remember from our last unit, we think of the derivative as being the slope of a tangent line. So if I look at the line y equals c, or f of x equals c, we know that's just some horizontal line, and so if we are asked to find the derivative, or the slopes of the tangent lines, you would see all the slopes would be 0. And therefore, the derivative of a constant is equal to 0, and we can use that doing Leibniz notation or f prime of x. Okay, how about x? So again, if we think graphically, we just know that line is our identity line, and we know the slope of that line is 1, so all the tangents will be 1. So we can guess that our derivative is 1. If we want to use the limit definition, we know that we're going to do f of x plus h minus f of x all over h. And so in this case, x plus h is x plus h, f of x plus h is x plus h, and f of x is x, and as you see here, the x's go ahead and cancel each other out, and then we have the limit as h approaches 0 of h over h, which reduces to the limit as h approaches 0 of 1, and the limit as h approaches any number of a constant is just that constant. And so our derivative of x is 1. Okay, let's up the ante a little bit and let's do x squared. Okay, well the derivative is going to be f of x plus h, so x plus h quantity squared minus f of x, which is just x squared, over h. We go through and FOIL that top out. To xh plus h squared minus x squared. And then we start canceling things off, so you can see the x squareds are going to cancel off. And then an h comes out of everything. And so I have the limit as h goes to 0 of 2x plus h. And as h goes to 0, that'll go off to 0. And therefore our derivative of x squared is simply 2x. Okay, let's go one more degree. Let's try x cubed.
Report to the office for a message. Shantavia Freeman Andrews, please report to the office.
Okay, so I do x plus h quantity cubed minus x cubed over h, and we can FOIL that through and distribute, or we can use Pascal's triangle. It's easy. Okay, and we FOILed some cubes last chapter, so hopefully we've got that cubic down. Now we have the idea that the x cubes go away, and I can take an h out of everything. Again, if you don't know Pascal's triangle, do it by brute force, that's fine. So I am left with 3x squared plus 3x plus h squared. And as h goes to 0, this will run off to 0, this will run off to 0, and we will be left with 3x squared. All right, some of you might have noticed a pattern, right? X cubed became 3x squared. X squared became 2x. X became just 1. So if we are to use that pattern, what do we think this is going to be? All right, so maybe you've got an idea, maybe not. Let's see if we can prove it. So everywhere there's an x, I put x plus h. All right, and we'd have to go through here. We can just use what we call the power rule. And the power rule is going to tell me all I do is I bring that power down and I reduce the power by 1. So the derivative of any x to a power is just going to be bring that power down, reduce the power by 1. All right, so some examples here. X to the 6th is going to be 6x to the 5th. X to the 1,000, 1,000. X to the 999. X to the 1.4, 1.4. X to the 0.4. Okay. Some other ones, they don't look like power, but we can rewrite them so that they are powers. I can write 1 over x as x to the negative 1. And then when I take the derivative of that, I take my negative 1 down. And then I reduce this by 1 power, so I subtract 1, which leaves me with negative 2, which can also be written as negative 1 over x squared. Either one of those are acceptable answers. If I take the derivative of 1 over x squared with respect to x, I can rewrite that as taking the derivative with respect to x of x to the negative 2. If I use my power rule tells me to bring this down. So negative 2x and reduce that power by 1 leaves me with negative 3. So negative 2 over x cubed. Either answer is acceptable. All right, again, the idea is to try to see these as power rules. So I'm going to rewrite the square root of x as x to the 1/2. And when I take the derivative of that, that becomes 1/2 x to the negative 1/2. Again, pull the power down, take 1 away from 1/2. You end up with negative 1/2. Again, that can be rewritten as 1 over 2 root x. Similar. Okay, try this one. That is the same thing as taking the derivative of x to the 2/3. Remember, people on power are on top. And roots grow in the ground, so that's on the bottom. And then I apply my power rule, which tells me to bring my power out front. 2/3 x, reduce that, so 2/3 minus 1 is the same thing as 2/3 minus 3/3, which is negative 1/3. Okay, and if you're looking for a different way to write that, you can write that as 2 over 3 cubic root of x. Remember, negatives are really fractions. Anytime you see a negative exponent, think fractions. All right, so we got a couple rules here for our derivatives. If we have a constant times a function, then that is the same thing as the constant times the derivative. So if we're taking the derivative of a constant times a function, it's the same thing as taking the constant times the derivative of that function. All right, let's prove it. Okay, so we know our definition is f of x plus h. So everywhere there's an x, I put an x plus h. Minus f of x, which is, in this case, c times f of x, all over h. Now, if you look at the top, I can factor out a c because they both have a c in them. So I can do c f of x plus h minus f of x all over h. And then we got to go back to our limit laws that we learned our first chapter, which tells me if I have the product of two things, I can look at the limit of each one separately. So the limit as h approaches 0 c times the limit as h approaches 0 of all of this stuff. All right, and the limit as h approaches 0 of c, so any constant's horizontal line, the limit is always going to be c. And over here you can see, oh, that's the definition of the derivative. That is f prime of x. And so we proved the derivative of c times f of x is the same thing as c times the derivative of f of x. Okay, so where is that useful? Here's my constant. Here's my f of x. What do? I can do 2 times the derivative of f of x. And so I know the derivative of f of x from the power rule is just 4 times x cubed. And so now I just put 2 times 4, which is 8, x cubed. Now I wouldn't write that in my next step. I would start to just say, oh, all I do is take my power, 4, times my constant, 2 times 4 is 8, and reduce my power by 1. And so when I go to do my second derivative now, I'm just going to take the 3 times the 8, which is 24, reduce that power by 1. We end up with 24x squared. Okay. The other rule we have is that if we're taking the derivative of the sum of two functions, we can look at that just being the derivative of one function plus the derivative of the other function. All right, let's prove this. Okay, so using my definition, everywhere there's an x, I put an x plus h. So this is f of x plus h right here. Okay, then minus f of x. So in this case, f of x is f of x plus g of x. Running out of space there. Move that over. Okay, so now you can see I've got my definition of the derivative set up. Now I'm just going to rearrange things. So the limit as h goes to 0. And I'm going to put the f of x's together. So f of x plus h minus f of x. And I'm going to put the g of x's together. So plus g of x plus h. And remember to distribute. So that's going to be minus g of x all over h. Okay. And now I can break up the fraction. Okay, so I can rewrite that as f of x plus h minus f of x over h plus g of x plus h minus g of x all over h. Right, because they have the same denominator, you just combine numerators and you'd put it over just the h, so we can split it up just like we can put it together. And now we use our limit laws. The limit as h approaches 0 of x, f of x plus h minus f of x over h. If we're taking the sum of two functions, our limit laws told us I could take the limit of one function and add it to the limit of the other function. This is a lot of writing, but I feel like I would be doing you a major disservice if you never saw any proofs, especially if you're headed on to some sort of math career, or you're going to be taking a lot of math in college. If you've never seen a certain math proof done before, and the first time you see them in college, it'll be a little bit challenging. You won't be expected to do these proofs on tests, but it's good to see them. So we know that the limit as h approaches 0 of f of x plus h minus f of x over h is really the same thing as the derivative, and similarly, this is the derivative of g. And so we took the idea of the derivative of the sum of two functions and showed that it was the sum of the derivative of those two functions. All right, so then you can see I have three functions here. And so basically the derivative is just going to be the derivative of the sum of all three derivatives. And we're going to use our power rule and our constant rule. So I take the 3 times the 5, which is 15x squared plus 12x. And the derivative of a constant, remember from the front, is 0. So obviously we don't need to write 0. This is so much nicer than having to go through all those limits and write them out. All right. Similarly, now we got some radicals and some negative exponents. Why don't you pause this and see if you've got the power rule down, and then come back and check your answer. Okay, so now I've got 8x, and I would write this as x to the 1/2. So it's 3/2. So minus 3/2, because 3 times 1/2 is 3/2. X to the negative 1/2. And I would rewrite this as 5x to the negative 3. So that becomes negative 15x to the negative 4. And you can leave it like that, or you can rewrite it as with all positive exponents, but you don't have to. All right, now I have something like this. Now you have to be careful because we have not said anything about having a function times another function. We've had a constant times a function, and we've had the sum of two functions, but we do not have a function times another function, and we can't make up our own rules. So an idea at this point would be just to go ahead and distribute. Okay, so if I do that, I'm going to rewrite this as x to the 1/2 times 3x plus x to the 1/2 times x to the 3/2. Okay, and now I know that if I'm multiplying, I go ahead and add powers. So 1 plus 1/2 is 3/2. 1/2 plus 3/2 is going to be 4/2, right, or 2. Okay, so have I taken the derivative yet? No, I've just simplified it differently so I can easily use the power rule. And now I go through here and do 3 times 3/2, which gives me 9/2. Reduce 3/2 by 1, so minus 2/2, right, which is going to be 1/2. And power rule here is 2x to the first, but again, I'm not going to write to the first power. Any questions that you have there, we'll be able to look at tomorrow. We are going to continue the power rule tomorrow in class. I hope this helps. Have a good night.